That's interesting. Thank you. Yeah, that used to be a button next to share screen. So I don't know. All right. Thank you. All right. So let's go ahead and share the screen. Okay. So it's recording. All right. So hit share. Okay. So now I'm going to go to the VM, as you can see. All right. And I'm going to open up the terminal. I'm just going to use the code as you had it before, right? So you can refer back to the previous lecture where we had completed the code, and then I'm just going to add the pertinent parts, and then you guys can ask questions if you have them. So I'm going to go to the desktop, but it's not that much code actually. Should be an XOR, I think. Okay. All right, so I'm going to copy CBC. I'll call it CBC XOR 3. .py. So this is exactly once I finish it, it'll be exactly what's already on the GitHub as CBC XOR 2. Okay. All right, so let's go ahead, get started then. So I've copied it. And now I'm gonna open this CBC 3. Oh yeah. .py. Okay. Just gonna remove the things, I guess, that I added. So that was added in the beginning. So somebody sent me an email saying, okay, I'm reading the files, writing the files, and should I change the code that we've already written? So the answer to that is no, right? So the idea is that use the code as is, this works, and instead just add, the read and write functions as required. So none of this, is my point, should have to be changed, okay? Remember, the key thing is that we create a list of cipher blocks, right? And so then we want to maintain that. So the easiest thing might be, wouldn't it be great if we could take a list of cipher blocks of byte arrays and save them into a file directly, and then send that to our friend, right? And then when we read it in, we read in a list of cipher blocks. Does that make sense? Back into memory, as if we just took a snapshot of memory, but put it in the file and then send it, and then we grab that from the file and put it back into memory exactly as it was. So that functionality actually does exist in Python, and it is achieved through a module called pickle, right? The pickle module, which is used, as I said, in production for things like companies like Hugging Face, etc. So they use this. Okay, so basically what I added was these two sections here. So I'm going to remove them, and then I'll just add them in again. So just to be exactly what you guys have in your code would be pretty much that. So that's the state of the code that we had last week, okay? Minus, I added like this print statement just to kind of know where everything is. This other print statement just to know, okay, this is after pickle. And then in here, I changed the name of this just to be more specific. Does that make sense? But everything is exactly the same code that we had done, okay? So it's exactly the same code that we had done. So if I was to run this just by commenting out these two items, it's not going to decrypt, but it should encrypt, right? And it's still doing the thing that I did, which is to take the byte arrays and converting them to strings and saving them to a text file. I gave you that approach because I thought maybe that's more like what you're used to. So hopefully you try to do that, right? But there's a lot of ways in which this can be done, in fact, okay? So let me go ahead and hit Control X, Y, enter. I'm gonna hit clear just to make sure we're back kind of where we were last week, minus the decryption. Okay, and there it is, right? So this is basically our cipher, and we are just saving it into a text file, but converting it to a string. So what I want to do now is instead, what if I just take this whole thing, which is a list in Python, and just save it? You know, take it from memory, save it into a file. So I'll add, as you saw, the lines of code that I removed basically. So I'm going to go back to the code. Great. So the first thing I'm adding is the library pickle. Okay, so that's pickle library. All right, so add that. You don't have to install it. It's a Python library basically. It's been around for like 15 years, 20 years. You know, it's been around for a long time. Very robust. Okay. After that, gen key that stays, decipher, encrypt and decrypt and encrypt stay. Okay. Encrypt message, that we've already discussed that. Decrypt cipher, we've already discussed that. Break message, we've already discussed that. And then we're here basically, right? So this is our message that we are encrypting. And here we read the message from, we can also read the message from plaintext cbc.txt. All right, so if you notice, I must have a message in there, which I can't remember. Oh yeah, it's something like, I'm reading from this file here, something like that, if I remember correctly. All right, so yeah, so we are reading that plain text file, okay? And then we print it here. So we are confirming, right? You read the plain text, fn.read, my message. I got rid of like these, the enter, basically, the new line character, and then we print out my message. So whatever is in that text file, and I would recommend that you get into the habit now of putting your plain text messages in text files, right? And just kind of makes it separate code from information. Probably a good idea. Right? We've talked about all this. All of this should work just fine. Remember, if you are, for now, we don't have to worry about the key, so you can just send that to your, your partner, email it, and they can hard code that in. That's fine. If you want to take it a step and add it as a file, that's great too. Okay. All right. So we do the encryption of the message basically, and this is where I provided this code for you to try encrypting, taking the binary, converting them to string, and then writing them out into a file. So we got as far as that, and then you just have to do the reverse of that. Okay. So it's a nice, fun exercise if you want to take that approach. The other approach that I would usually take here is to use something like Pickle, because we are doing cryptography, where basically we have a cipher all the time, and this cipher is always going to be a byte array or hexadecimal or something like that. So it creates complications. Also, we might be storing this in a list or something, and we don't want to change the algorithms, right? That's complexity. So definitely you don't want to change the code. So then to do this, we just basically need to take, we have to think first of all about the cipher. So if you take a look, the cipher is a list, right? Encrypt message gives you a list of cipher blocks. So every element in that list is a byte array, right? And we have seen that a couple of times. So let's try just saving the whole list, right? So let's try just saving the whole list. To do that, we are going to take advantage of Pickle. So this part, I'm just going to leave it here. It does it, right? It saves it as a string, but I'm taking a second approach, right? So this is like one approach, and this will be another approach. Call it the probably easier approach. So I'm going to create a file. I'm just giving it a name, file X, for instance. And I'm going to say open, right? And I'm going to specify the name that I want. So in this case, just to be, for this scenario, you don't always have to put the word pickle in there, right? But it's just for this scenario, I'm going to call it pickle cipher list, or pickled cipher list if you want. And so that basically should be the list of all your cipher blocks. Okay. I'm not going to put an extension. I mean, you could if you want, like bin or something. It doesn't matter really. And then here, one key aspect is we do write because we are writing, but you're going to see this is a very common thing. You put this write B, like write bytes or write byte array versus writing as a string. So that helps you out quite a bit. Okay. Then after this, I'm going to go ahead and use the pickle module. So it's called pickle. You call pickle basically, and pickle dump. Okay. So this is going to take the data and just, put it on the hard drive. So what do we want to send? What's the data? Cipher list, right? Yeah, exactly. Cipher list is the data, right? Oops. So cipher list is the data. And then we want to tell it where to send it. And that's going to be to that file X. And that's it. So it should be simple enough. Forget the close parentheses and then add just file x.close. It's always a good practice whenever you open a file to close. Okay. And that's it. So if we run this one, we should have now this file generated and it should have some data in it. Does that make sense? So now let's go ahead, Control X, Y, enter. Okay. Okay, no errors. That's a good thing. Hit clear. This is what we should have in there, right? So hit clear, ls-l, and there it is. Pickle cipher list. It has a size of 192. You can cat it. So you can do pickle cipher list. And as you can see, we can't read it because it's a byte array basically. So, but we stored it exactly as we wanted. Hopefully the list is there, everything. So it's like we took a snapshot of what was in memory and threw it into, so that's a very handy thing. So now what you have to do is send this to your friend, right? So you have to send this file, right, to your friend. Even if it's a list and somebody could like figure that out, the other information, the blocks are still encrypted, right? So that should achieve confidentiality for this problem. Got it, guys? Does this make sense? All right. You also need to share the key, obviously, as I said. Make sure you're not running gen keys every time, because if you are, then you're going to, it's not going to work. This happens a lot with students. I see this. They just rerun the code all the time, and they're not noticing that they're running gen keys again. And so now you have you're going to have a different key, and it's not going to decrypt, right? So you need to get that key replaced in the key and actually the initialization vector as well. So but that part you can just send to your partner. It's easy, just print gen key here. If you're having issues with, like little errors, you can also use pickle, right? So that's the beauty of pickle. Pickle now gives you, okay, how do I send the key? It's a byte array. Grab the key, pickle dump. Send them the file. And then what do they have to do? Read it in. Got it? And that way, that takes care of a lot of problems for you. Any questions? Huh? I'm gonna do it. I'm gonna do it. Any other questions? All right, so let's go ahead now and read it in. And it's kind of the similar process, actually. So let's go ahead down here. Okay. I'm going to add a new line here. Just kind of separate it out, but it should be very obvious. Should be like 3 lines of code. So I'm going to use a different file for this one. Just going to call it file Y. I don't like to reuse files. So file Y, I'm going to get rid of this green. Okay, file Y is open, right? And what do you open this time? The pickle file, right? The one that this is what you sent to your friend, right? This is what gets sent via email or something. So this is pickle cipher list. Okay. And then now, instead of WB, because we are reading, we're going to say what? RB, right? So read would be the common thing, but because it's byte arrays, we want, we're going to say RB. And that looks, oh, I'm missing a single quote. Good now. All right. Then we're going to use pickle again, but this time we're going to read in the file. I'm going to create a variable. I'm going to call it from pickle cipher list to distinguish it from those cipher lists that we had before, right? We want to make sure that we're using the one we just read from the file. So from pickle cipher list, we're going to read in. So you're going to use pickle dot. And now instead of pickle dump, we're going to say pickle load. And we're going to load in file Y. Okay, so that should take care of it. And then again, make sure to close the file whenever you open a file. Just like that, and that's it. You're done. If you notice, you basically this cipher list that you had here, right, in the encrypt should be equivalent to from pickle cipher list. You see, there should be the same, basically. It's like you took a snap, you went in RAM, took a snapshot of that, threw it into a file, then went to the file, grabbed that in, and just tossed it into from pickle cipher list. But it's the same. Okay, and it takes care of so many things for you. All right, now that we have done that, we can enable these sections over here. So I'm just going to, so if you notice, this was just a decrypt cipher, right? So this is just our general function that had worked before. It works with a list of byte arrays, and we have a list of byte arrays, and we didn't have to do any modification to our code or anything like that. This is, highly recommended for this kind of thing. All right, and then we have our key and then our initialization vector. Just remember, because you're sharing that with your friends, if you're having issues, probably use pickle also and save those, because they are byte arrays from the gen key function, right? If you look, gen key returns a byte array. So, all right, that's it. So now let's go ahead. So we should take, if you notice, we're taking from pickle cipher list, which is what we got from the file, and we should be able to decrypt it, right? And then print it out, and it should print out a string of characters, which is as far as we got it, so that we could at least read it. All right, so now I'm going to go ahead and hit Y. I'm going to hit clear here. You can go ahead and hit, yep, here. And there it is. After pickle, you can see my message is here, and I am reading from a text file for the CBC example, right? And if we do ls-l, it should be that the plane, right? So we should do cat plane. My message is here, and I am reading from a text file for the CBC example. And that's it. Any questions? So you should be able to complete the assignment with this. As I said, the only thing, if you're having trouble with the keys, you're going to have to repeat the pickle read, pickle dump procedure. Okay, you have until Sunday to complete this one, I believe. Any questions? Please make sure, as I said, very important, work with your partner, understand what you're doing. Achieve confidentiality. You need to send a file. I want to see your email screenshots, right, of how you show that you did it. All right, that I can stop the video now, right? That was it for that part. So I'm going to go ahead and I'm going, how do you pause? Okay, so it's recording now. I'm going to share the screen. Okay. All right. So as I was saying, I'm going to continue the lecture of RSA. We're going to do problems like we did last Tuesday. But today we're just going to start playing with this algorithm. So this should be fun because if you ever wanted to know everything about RSA, it's here, right? It's like everything, there's no libraries being used here for abstracting the algorithm. Everything is from scratch, right? So it's nice in that sense. You can really get a sense of what RSA is just by looking at these. This is not like the toy example where we were just encrypting like 7 or 14. This has helper functions so that we can give it a string text and actually encrypt with RSA. Now, remember, of course, RSA is meant to be used just for encrypting keys, you know, like the block cipher or symmetric keys, not really for encrypting large pieces of text. One of the exercises that we will do is that you will generate different sized keys, okay? And then you will see by increasing them how long it takes, that you'll see that it's slower. If you remember, when we did the toy example, which was a toy, when we did that cipher to the D, that was a very large number that if you tried to compute that on a calculator, you just couldn't, right? So, and that was like very basic numbers, but you tried it in Python and you were able to compute it. Well, now you're going to be creating really large numbers, okay? And so this is what this script can give you. Does that make sense, guys? All right, so let's go ahead. What we need is this one, right? So this Python script, I always provide here so that we can start to fill it in, okay? Just keep in mind the final one is on the GitHub already. All right, so I'm going to go ahead and download it. Okay, so it should have gone to downloads. It's not that. Maybe it goes to the desktop. Actually, it's asking me where to put it. Save. Let's save it. Okay, let's see if it put it on downloads. Yeah, there it is. Okay, so it's in downloads. Okay, and that's all we need. Okay, guys, you don't need anything else. We're just going to modify this one. So we can go ahead now and close this. I'm also going to close bright space. All right, so let's do clear here. Clear. All right, so I'm going to copy that script. So I'm going to do, no, I'm going to, oh, I think I already have an RSA folder right in here. You guys can see this, right? Yeah. All right, so ls-l. So we were doing the RSA mod. That was problem number 1. Also, I guess, yeah, so now we're just going to add that script in here. I'll do Ph.D. So then I'm going to do CP home seed downloads, right? Downloads. And then the name of it was what? Lab week 4. Lab. Lab week 4. Okay. So that I have it now, and I'm just going to copy it in here, and I'm going to call it RSA full code. .py. Okay. Okay, so I'm going to do clear /l. And so now I have my code in here, and I can proceed to start to modify it, right? So I'm going to modify it in here. And yeah, that's the idea. Any questions? If I try to run this right now, it won't run because there's a lot of things that are incomplete. See, it's giving me some errors. Okay. So we're going to fix those. Got it? Okay. And we're going to go through, but initially I'll give you an overview of it. This might take us this session and the next session, the next lab session to complete. It's very important, I think, to go through it. Okay, so we're going to open it now with Nano. And there we go. So this is your RSA code. It's got a few functions like random, right? Obviously, this got iterative tools. It's got some math like log 10, things that are needed by the algorithms, time, etc. As I said, we don't have to do anything with the algorithms except use them. So for instance, whenever you need a prime number, you don't have to write the code from scratch to generate a prime number. Instead, you just use the function get prime, where n is going to be the size that you want. So this is where you're going to modify it to be 10 to the 1024 or 248 or 4096. Each time you do that, you can convince yourself by printing the prime number that it's bigger and bigger and bigger. And you will see the effect. It's going to slow down. Make sense? All right. So, I mean, if you've ever wondered how to write the code to generate prime numbers, you can see it here, but that's kind of outside the scope of what we're doing. We're just going to use the function as is. Okay. That's it. Make sense? And then this in function that you see here is going to be the thing that we use for calculating D. So it's going to be that part of the algorithm. So if we go back to how RSA worked, do you guys remember how it worked? We needed P and Q, then calculate N, then calculate phi, then we would get E, then we would get D given a formula, right? So all those steps is what we're going to be doing. And then once we have the keys, the public and the private key, what do? We're going to actually encrypt and decrypt the message. We're also going to need some helper functions to convert from like text to numbers and all that kind of thing. So this one, I will just start adding comments here, and I strongly recommend that you guys do the same, because I've written this a little, I have this a little bit differently so that you guys, fill in. It's like a puzzle type of thing. So I didn't use the exact same variable names that we've used, and you kind of have to figure out what everything is, okay? But I'll say this one is, to get the D exponent, okay? Which you should know what that is, because that's the whole point, right? Understanding the algorithm, okay? So notice here's the multiplicative inverse is what this is called. And then here's one of the algorithms that I told you about, the extended Euclidean algorithm, right? Which we mentioned. And, so we're not going to go into that depth, but there are some algorithms that people invented that are the ones that help you to find D or other values, okay? But if you want to, there's no reason why you can't go line by line and kind of figure out how everything works, because it's all written from scratch. Gen RSA, as you can see, I've left this. Gen RSA P and Q generate public and private keys. So you should understand from the algorithm how it works. If you notice, I have in there this section to be completed by student. So you guys have to implement the idea, get P and Q, all that. Got it? Make sense? All right. Various utility functions. These are just things that will help you to convert a text string to an integer, convert an integer back to a string. Obviously, because we're encrypting strings, we're going to need to be using some of these, right? You can just have them as is. They're actually used by other functions in the code, so we may not even have to worry about them. Here's the encrypt function. So this would be the what? C is equal to M to the E mod N, right? So you need all those parameters to be able to compute those things. So you encrypt a message with the public key. What is the public key in RSA? Oh yeah, but what letters is it? Sorry, what letters in the algorithm? E comma N, right? So remember that. Okay, but N is made up of P and Q. So remember that as well. Okay. Decrypt, you can see that here. This is where we decrypt message with a private key. And this uses another algorithm called the Chinese remainder theorem. All right, so just different algorithms that are used to compute these things more efficiently. Because this is written in Python, instead of C, this is also slower, right? So Python is slower than, say, C, C++. But it's more accessible, obviously. If you want to print the ciphertext in hexadecimal, you can use this function. So there is another helper function. These just work. Don't touch them or change them. You don't have to, okay? All right, and then this is the main section, as you can see, main to be completed by a student, this section as well, right? So it's basically implementing the RSA algorithm as we started to discuss it in the last lecture day. Questions? All right, so let's first do some some verification of the code. Let's just look, because I did see it had a little error somewhere. Let's take a look. You guys are seeing this, right? Yeah. So these are the libraries. They look fine. All of this looks fine. All of that looks fine. That's for generating the prime numbers. So I'll show you an example in a second of generating the prime numbers. Let's take a look at this one. This one looks fine too. GenRSA, this will probably give you an error because there's nothing in here. So just put a return. Okay. You just kind of, for that. Here, we're just converting. Okay, these should be fine. You guys have any questions? These should be fine. Encrypt should be fine. Decrypt looks okay. Here's a print statement. All right, in this print statement, print in the function print hex list. Okay, yeah. Go into this function here, and add a 0, okay? Like that. So add a 0 in there in the function print hex list. That should take care of, it's a formatting issue. And that should be the only thing that needs to happen. Got it? Pretty easy, right? It's just a formatting thing. All right. Print, this is fine. This is fine. Yeah, I think that's the only thing to worry about. Oh, there's another print statement. Go to mod, one of the other helper functions does have a print statement. Yeah, this here. Oh, it's not a print statement, but a formatting. So this is the same thing. You see that? Just add a 0 there as well. So in the mod size, add 0. Also for formatting. Okay, got it? So those two corrections should be all you have to do. And then after that is just understanding the algorithm and incorporating it into this code, okay? So I'm going to run Control X, Y, enter. I'm going to run the code again. There's, oh, print done. Yeah. So let's find this error also. That should be at the very bottom. Yeah, I'm missing a parentheses here. So just do this. And that. Okay? Everyone got it? All right, so try it again. Okay, it's gone. Good. Okay, good. All right, so now we can go back to the code, and now we can start the actual implementation of our algorithm. So we want to start thinking about the steps, right? So this is where you're going to write the logic. This is where you're going to need to have a text message that you're going to try to encrypt. So let's see how we're going to proceed with this. You know, probably the most fun thing that we can do here is to generate the prime numbers first, right? These are prime numbers, but they would be pretty big prime numbers, right? So let's say we need a seed value for the prime number. Seed size. And we're gonna, or size, sorry. Seed size is fine. For the prime numbers, you can also call it size prime numbers, okay? And make that some value like 512. But what I want you guys to do, as once you finish everything, is I want you to try incrementing the size and see the impact on performance. So for instance, you can start at 256, then work your way to 512, then try 1024, 2048, right? What would be the next one? 496, right? I think. Yeah. All right. So try all these numbers. And what you're doing is you're generating bigger and bigger prime numbers. I think P and Q have to be multiplied to create N. That's even larger, right? So it's gonna get really big. All right, so let's now that we have this, let's generate some prime numbers. Okay, so I'm gonna do prime P and Q, right? And now we can invoke the function get prime. You guys see that? And in here, we're gonna plug in the seed size. So basically we're saying the seed size should be 512 for our prime numbers. Okay, so then I'll start at 256 actually, just so that we can see the effect. And we're gonna print the prime numbers. So then also Q, you can do basically it's gonna try to generate random prime numbers of this given size. So then we can do get prime seed size. Obviously, P and Q cannot be the same, okay? The larger N is, the slower it will be to compute the prime numbers, okay? So you get a bigger impact. So let's go ahead. Since we have this, let's see if we can print P and if we can print Q. That's our goal. Okay, got it? Any questions? All right, so we're gonna hit Control X, Y. And there you go. And you're just having fun with prime numbers. That's 256. Those are the numbers that you get, okay? And, you know, that's the idea, basically. Now, of course, I'm not going to do this part, but what I want you guys to do is to go through the whole process of encrypting, right, and decrypting, and changing these values so that you can see that it takes longer and longer to do the encryption and the decryption. But for now, I'm just going over the prime numbers themselves. So I'm going to go over here and I'm going to change the seed size to 512. You guys see that? 512. Go ahead. Print it. Did it change? It did, right? Think about how astronomically big these are. And we still need to multiply them. And after that, you know, get D and then take C to the D. This is really big, okay? Let's try another one. So then we're gonna do 1024. Oh, my, just need to get my charger. Right. So now, let's try 1024. Okay. So I'm going to go ahead, Control X, by Enter. See? You see that it took a minute? It slows down, right? And so you start to see the impact on the hardware, right? And cryptography, I think we had one in one of the slides that today is like 4096, right? That's what they're using for the size of these things. So imagine how big, they need to be so that you don't break them. Because remember, the trick is, what are we printing? P and Q. P and Q will become N by multiplying P times Q. N is part of the public key. So you have E comma N. What somebody wants to do, an attacker, is what? Take that N and factorize it and get P and Q back. If you can do that, RSA is broken. This is the trick for the practical exam. I will give you an N in some way. You will have to factorize it. Now, you don't have to factorize it by hand, right? You'll use what? FactorDB. Remember I said factordb.com, right? That one will just give you the values. Obviously, I'll use something within that scope, but something like that, it can't do, right? So that's the whole idea. Does that make sense? And so this is important so that you understand, just like we did an example last week of how to break stream cipher, the OTP. Now RSA is also how do people want to break it, and this is how they do want to break it. I mean, it seems like a simple thing. If I have P and Q and multiply them, I have N. I know N, so obviously I can get P and Q, right? But the whole security of RSA depends on that. It's difficult. All right, so let's go ahead and try. Let's try a bigger number. So I think I tried 1024. So now do 2048. And currently, all we're doing is computing the prime numbers. We're not even doing encryptions, decryptions, or anything like that. All right, so you can see it's taking a while just to compute the prime numbers. Still going. So gets big. Now, this is obviously done in Python. Python, as I said, is great for understanding things, for prototyping. But if you're actually implementing this as an application, you would do this in C++, which is what OpenSSL is, right? So you'll use, a much more efficient set of algorithms to compute this quickly. You can see basically it's taking too long. Obviously, we're running on a VM, so that might have something to do with it, but still. That's one key thing with cryptography, is I think I've mentioned several times, it's a balance between security and performance. Okay. So you can start to think, okay, I'm not going to encrypt my entire Marvel movie that I get from Netflix with this, right? It's too much. So instead, you encrypt the Marvel movie with CBC, AES. No worries, just use that key, the secret key, a long one. Very efficient and fast. And you use RSA only for sending the key, which is the problem we've had for the first third of the semester. You guys just didn't know how to send that key to your friend, right? So that was the whole idea. So that's what this does. But if you notice, you only have to do it one time. Once the key is exchanged, boom, use AES. That's SSL, actually. So SSL is now the combination of these different technologies and algorithms. Got it? All right, so it's taking too long, so I'll leave this for you guys to, like, you know, go get some coffee and try it. I'll kill it here. And obviously, I'm just going to use a smaller key. So I'm going to go back to 512. I think that's a good size. And we should be able to follow along with the exercise, you know, and get the feel for this. But, you know, this should be fun. All right, so let's do 512 here, okay? And we know that works. So we can just save it. All right. So now I'm going to, so you know the size of 512 and all that. You have a sense of how that works. So again, you know, we've used one function, all that code, just we use it as is. Okay. Now, what are we going to do? So you've got P and Q, right? So we've got our key there. And then what do we want to do is encrypt something, right? So how do we do this? Well, I mean, you should probably read from a file, right? And you know how to do that already because it's Python, it's the same code. So I do recommend that you create a plain text file, put your message, your plain text message there, and then read it in here, right? But I'll just hard code it. So I'll do, you know, the plain text will be what? Let's just call it plain text message, I guess. So plain text, plain message. Okay. And this can be anything that you want, but in general, it would be the secret key. So now, I'm not saying this is homework, but for the CBC AES homework, right, the one that's due Sunday, you have that key, right? Remember? How would you send that key? Here. This is where you would send that CBC AES key. You guys see that? That's it. Okay. All right, but let's just put in a message so that we know that it works. So in this case, what I may do, just again, I'm telling you, like I'm literally telling you how the practical will work, right? What I will probably do is here, this is the message that I will hide. Okay, or it could be a key. And then or it might be a key, actually. It makes more sense that it would be a key. You will need this key then to decrypt with AES CBC, for instance, okay? So I will probably hide the key here. The key to this will be that I am not going to give you P and Q. I may give you N somewhere. You will need to factorize it and plug in. Once you factorize N, right? It should give you P and Q, and then you would plug them in here, and then maybe that's how it's going to work, okay? So remember. All right, good. So now let's just think of some message to encrypt and decrypt here. Okay, Claude Shannon. Shannon is the father of cryptography. Right, something like that, right? So let's some message. Just remember, I'll even add a comment here. This is where the where the AES CBC key would go. Okay. And then the initialization vector, that one, you don't have to encrypt technically. You can just make it available to your friend via email. But this definitely, the key definitely needs to be encrypted. Got it? Yep. All right, great. So that I just added some message. Don't put such a long message here because it's not really meant for that, right? And you might start to find some errors in the algorithm. All right, so I've got the plain text message. What else do I need? I need to generate my public and my private key, right? So there's a function already, gen RSA, somewhere in here. And this is what I want you to use to generate the keys. So generate public and private keys here, okay? So this is what we want to do. So then gen RSA would be the function that you would invoke there to get the key. So we're going to say gen RSA. Again, gen RSA only needs to run once. You don't have to run it every time you're encrypting and decrypting, because then you're using different keys every time. Make sure that you keep that in mind, right? Especially because with public and private key, you have to make your public key available to your friend, right? So that means that you can't modify that all the time once you've made it available. So the algorithm, the first step was to calculate two prime numbers, and from there we would compute everything else, right? So it makes sense that gen RSA should take both of our prime numbers, right? P and Q. So it should return the public and the private key, right? And here we have a choice of how we're going to write this, but it would be what? The public key is, so we can actually write it like this. So public key as a tuple. So public key in RSA is a Python tuple of E comma what? E comma what? N. Very good. E comma N. And then the private key is a combination of D comma N, right? So in general, sometimes because it's private, you can technically, to make things easier, you can have P and Q there. Do you see that? You obviously cannot make P and Q available here, right? You get that, right? If you made it available in the public key, you can't. But in the private key, it is an alternative to do that because they're private anyway for computational purposes. Got it? Any questions on that? Nope. All right, good. So you can write it either way. I'll write it like this for now, but I may choose to rewrite it in another way. As long as it's kept private, there's no issue. All right, so then that means that gen RSA should probably return E, D, and N, right? Got it? Okay, so now then we want to go into gen RSA itself. I can save this just so I don't lose it. Okay. Oops. And we're going to look at gen RSA and think about how we're going to approach this one. So as it turns out, E can sometimes be chosen to be a specific number. You will see this. Depending on the size of the prime numbers, there's actually a fixed value for E. But N is still different, right? So it's a combination of E and N will always be, whatever the prime numbers are, but you can always kind of pick a set of E's that work pretty much all the time, okay? And so this is kind of what I will show you here as well, that we don't always have to calculate E. We can just use one of a set of E's that will work. Depending on what's important is how big are our prime numbers, because it needs to, you need to be able to compute it. All right, so then we're going to go to gen RSA and think about the logic. So it should be pretty straightforward, at least the very first part. You can do N, right? So we can go over here. 1, 2, 3, 4. N is what? P times Q. You guys see that? And then if you remember, I was going to call this other variable phi, just like this. And what was this one? P minus 1 times Q minus 1, right? If you remember. Okay. All right. So I got my phi, I've got my N, and then now I just have to calculate D really. Okay, I have to calculate D so I can have all the parameters that I need. So to do this, we're going to say if N, so this is where the size comes in, right? So if N less than 65,537, so if it's less than that, then we can just use the value 3 actually for E. So 1, 2, 3, 4. Then we can say E equals 3. Do you see that? Okay. Hit enter here. Else, now if it's most likely it will be, right? N will be bigger. So then in that case, we need to use a bigger number, but we can also use one of a set of very well-known E's, which would be that same number. So it's going to be E equal, oops, sorry, not there. 1, 2, 3, 4. So E will be 65,537. And we can just use that. Okay. As it turns out, the math still holds, and we can just keep it a little bit more consistent. And we already know, right, which is going to be, we already computed it. So in here, we can add a return that returns our values. So we're going to, oops, I'm going to say return. Okay, and we're going to return basically a triplet in Python. So we just have to make sure we write that correctly. So it's going to be E, comma. Actually, let me just do this once. I'm going to go down here. And, oh, I already had a return, right? Yeah, let's do it here. So I'm going to return E, comma, D, comma, N. So I actually already have 2 of those 3 terms. Right? I already have 2 of those 3 terms because I already computed N up here. I computed E here in the if statement. So all that remains is I need to compute D. If you remember, this was that formula D times E mod phi equal 1. Remember? We talked about that. We did some of those exercises by hand. But of course, something like that, you're going to calculate with a function, with an algorithm, right? But that's really the next part. So this D term, we're going to use a function that we have somewhere here. This one, in. If you to get the D exponent, we're going to use this function in, okay? So if you remember, D times E mod phi takes E, so we need to provide E, right? We're calculating D, and the other variable that we need to provide is phi. Phi we know is basically P minus 1 times Q minus 1. So instead of providing phi directly, we could provide the P and Q, but we've already computed phi. Got it? Do you guys understand what I'm saying? Want me to repeat it? So D times E mod phi. So, okay, I'll write it here. So the formula was D times E, the modulus operation, phi equal 1. This is the relationship in RSA that needs to hold, right? But we're going to use this nice function here to compute that for us. Did it? All this time?
No,
like
no, just that.
All right, great. So as I was saying, if you remember from the lecture, we'll do more exercises of this, right? But if you remember, the relationship was d times e mod phi equal 1. You've already done this modulus operation in a previous problem, so you should know this is just 1. So really, we just need to provide phi or phi and e, and then we solve for d, right? That's what this function here should do. Now, this might be confusing to you here. It says p and q, right? So you might assume it's the prime numbers, but it is actually e comma phi. Okay, so just change that if you'd like. That's perfectly fine. But just be consistent if you're going into the algorithm. So I would just leave it actually. All right, so let's go ahead and think about this, right? So then we need to, in this example here, we invoke the inv function, and we provide to it e, which is 3, comma, phi, which we already computed, right? We compute it here. And then in this one over here, oops, sorry. And in this one over here, we call inv again, but this time around, we provide the other e, which is 65,537, and we provide e. Okay. Like that. Perfect. And that should give us the 3 variables that we need. And, we just use the functions. We let the functions do the heavy lifting. If you notice, as I said in the function inv, it uses the extended Euclidean algorithm to calculate these values. So we don't have to worry about it. It's just specific algorithm. Okay. So that should be it. So now we're going to proceed to print this out. We've got, so I would think that we have all the variables that we need to generate the keys, okay? Generate the keys. So I'm going to go ahead, I'm going to go to the main section again. Okay, and let me just double check how I'm generating these. Yeah, so should be correct. And I'm going to print them, I guess, just to view. That might be a big thing. Let's just run it before we print it. Okay, so let's just do Control X, Y, enter. Oh, I wrote that without a comment. Sorry. So just add a comment here. So I was writing the equation there. Okay, so do it again. All right, good. So everything ran without errors. So now we're going to proceed to just look at some of these parameters, see what we can view. But we've got our public and our private key, okay? In this scenario. So we're going to scroll down. And now we're going to try to print the parameters of the key. So these are separate values. So we're going to print n first. Think about that n, right? So it's the multiplication of p and q. Oh, could be big. Okay, so you can see p and q are these, and n is this one, right? Pretty big. So this is P, this is Q, and this is N. So you can see how RSA depends entirely on using really large prime numbers. Any questions about that, guys? Okay, so let's print out the other terms. We're going to print E. So what would you, okay, so let's say it's a multiple choice question, E and D. What would you say about the sizes of E and D? E greater than D, D greater than E, the same? What do you think? We can see it here, right? Print E. And we can probably try print D. Is that correct? Okay, so let's try these. I'm going to hit clear here, actually. Okay, so we're going to run this now. So what do you guys think? So which one of these is E? Small one, right? 65,537. We already had it, right? Look at D compared to E. Does that surprise you? This is how it should be. So D is always going to be much larger than E. Okay? Remember that to compute the cipher, we need to use both E and N. And you do have N. And N is a large number, which is this one, right? What you keep private is this one, right? This should not be available to anyone, or the prime numbers, definitely not. What the hackers want to do is they will have N. So they need to factorize it into these two terms, and then they could break the whole of RSA. Is that clear enough? Yeah. All right, good. So we are at a point where we have, generated our public and private key. So you have gen RSA. Okay, so now what do you need to do to, if you're working with a partner, remember each of you now needs to do this, right? So Nathan and Tim are working together, right? You guys need to run gen RSA once and do what? You generate your public and private key, and you generate your public and private key. Got it? And then you need to share these keys, make them available to the world, send them via email. So looking at this data, what would you send? Like, let's say this is one person, let's say Bob. So what does Bob send to Alice? EN? ENN. So which ones are those here? You do not send this. You're gonna get, they're gonna break. That's D. You do not send D. You do send E, right? Which is this one. And this is P. All right, let me like highlight it again. This is P. This is Q. This is N. This is E. This is D, which is much, much larger than E. So again, if this is Bob, what does Bob send to Alice? ENN. So E is this one, right? And which one is N? Right above it. The one above it. Very good. This one. That's what you send. Okay. And never these. So that's why you want to like automate this process, and you just generate, this is my public key file, this is my private key file, maybe use pickle again, and then just send them the public key. Okay. And then they can pickle load, and then they'll have them. Got it? Pretty easy. All right. So again, I leave that part for you, but start writing that code, right? So you're going to generate these public and private keys because you have to share this secret with your friend. Because now in the future, you might get a problem where I ask you to do CBCAES, but now you must exchange the key securely because you now can do it for the first time. All right. Any questions, guys? All right. So Gen, I think let's look at the code again. So I think Gen RSA is done basically. Yeah, so Gen RSA is done. We printed the keys. So here I'm gonna write a comment. So for you guys to start work, this is not homework yet, but I want you guys to start doing the same thing that you did for the previous one. You know, write to file. Maybe using Pickle, which you learn how to use today. All right, use it as an exercise to practice. And yeah, start. So I'll stop the video here. In the next session, I will go over, since we have the keys and everything, we can start encrypting and decrypting basically. So we'll go over that, and you know that will be in the next Thursday lab. Okay. And I'll go over a little bit of more theory on Tuesday about RSA, more, you know, problems by hand, etc. And yeah, we made really good progress today, actually, on the algorithm. Okay. So this will be kind of, so let me stop the video.